you know you always wanted to learn about orbitals. So today we're going to be talking about orbitals, and hopefully by the end of this video you should be able to fill an orbital diagram and also confidently draw orbital shapes. Today's timeline looks like first we're going to talk about orbital shapes. What are the shapes and how they can be drawn? And then we're going to use that understanding to fill an orbital diagram. We also need to learn what an orbital diagram even is, a few things that go hand in hand with them, like the Pauli exclusion principle, spins, ups and down spins, and then we can fill those orbital diagrams and use the diagram to predict the charge of an atom. So I have a really favorite video. I truly love this video. And I have the link in the description below, but I want to give you just a snippet of how fantabulous this video truly is. So there's the S orbital, and you can tell that there is a circle that was in the center. Now these are the p orbitals along the x, y, and z axis. Orbitals. Now we're in the d orbitals. They kind of look like clovers. That's along the x and z. This is still D along x and y axis. Also D along z, y axis. And now we're also looking at x squared, y squared axes and z squared axes. That's a weird looking one. Okay. Orbitals. So now if we put them all together, there's S, P. Now we're putting in our D's. And you can tell that this is filling up quite well. Looks like an atom now. Whoever made this video, thank you from the bottom of my soul. Thank you so much. Now that we saw how the orbital shapes can all fit together in 3D space along an X, Y, and Z axis, that'll give you a better idea of what we're getting ourselves into in being able to draw these. But before we do that, you should probably have a general idea of what each shape stands for. The S sublevel, or the S shape, the S block, if you watched my previous video on electron configurations. If you didn't, please go back and check that out. Electron configuration card popping up there, and also link in the description below to catch yourself up on that information as well. But the S sublevel, that S shape, is a spherical region. So it's a sphere, and it gets increasingly larger. So if you look at this image here, we have one S, and you can see that that's a much smaller sphere. If you go all the way up to 3S, you can tell the sphere has grown substantially larger. So as we go down those levels, the energy gets bigger and bigger, the atom size gets bigger and bigger, and so what we end up with larger and larger spheres. So if we're looking at our periodic table, if this is our S block, this would be a pretty small sphere. But if we go down to level 7, these would be pretty big S spheres. P sublevel is also pronounced pi, so hence the pi on the screen there. Pi. The pi sublevel can be a figure 8 most of the time, so it kind of looks like this figure 8 shape, or like a peanut, which is why I put the peanut right next to it above my head. So it kind of has that peanut shape, and that peanut shape can be along the X, Y, Z axis, all three. So the thing to keep in mind here is that there are actually 3 figure 8s on this pi level. So the 3 orientations that we're looking at are for X, Y, and Z in that peanut shape, or that figure 8 shape. All these are nasty. I'm doing this for you. Oh. Oh, this is disgusting. Dollar store latex. Okay, that's horrendous. So if we were going to visualize the P or pi sublevel, those shapes, we could think of it as balloons. And I want you guys to actually envision balloons in your mind anytime we're talking about these orbitals. Now, these orbitals are in 3D space. So if we're thinking about an X, Y, and Z axis, so I want you to imagine an X and a Y in front of you, and then the Z coming like this, out at you and into you. So right now, if I was going to hold one of my orientations for P, my figure 8 right here, this would be in my Y orientation. Then of course I also have an X orientation. And this is going to be very difficult to hold here in a second, so don't judge me. So we've got an X and Y, but we also have a Z. Now remember, Z is coming out at you and back into you. So we have orbitals also coming out at you. These are going to go everywhere here in a second. Oh my goodness. I don't have enough fingers for this, guys. Okay, there we are. So we end up with this kind of like clover looking thingy, which is what this is supposed to represent down here. It's supposed to represent what I'm holding in my hand. This 3D, and if you can see from the top, you've got like one coming out at you this way. You could have 4 in the plane that way. In the plane meaning flat, kind of like versus you, it's flat, right? One that's pointing away from you and one that's pointing into you. That would be this one back here. So this would be all your P sublevel. Now remember, a max number of 6 electrons can fit in this configuration right here. The D sublevel is kind of shaped like a dumbbell. So you can think of S for sphere, P for peanut, D for dumbbell, or daisy, because it kind of looks like a flower to me. So there's also dumbbell, daisy for D. This has 5 possible orientations. So 1, 2, 3, 4, 5. 5 possible orientations that the D sublevel can fall into. Again, think of the D sublevel as dumbbell. So this kind of reminds me of a dumbbell, like what you work out at the gym with. Kind of looks like it. I don't know. Maybe that looks like a, I don't know, a caveman's bone. I'm not sure. Whatever. And then you've got a daisy right here, like a flower, right? Pretty flower. Wow. I know my art is stupendous. Notice that the daisy is also in the different orientations of the XYZ plot, and the dumbbell, the one in the middle, is really the only oddball out, where it has this weird ring donut around the middle. Hey, look, there's another word. So you've got D for dumbbell, donut, daisy. It's kind of dumbbell donut. Those go hand in hand, right? You go work out with dumbbells and then you eat a donut? Question mark? The last sublevel is F. Those are your inner transition metals. I endearingly refer to this level as the F that sublevel. Don't even ask. Like, the level of complexity for the F sublevel, I sincerely hope that you would never have to draw this. It's just insane. There are too many orientations to even wrap your head around to be able to draw this in any feasible way. So think of the F sublevel as the F that. Oh my gosh, there's no way I'm going to draw that over my dead body kind of thing. But the F sublevel has all of these orientations that you can see here, and also a weird looking dumbbell version with 2 donuts as opposed to 1 donut, like the D sublevel did. So here's another video that kind of pieces all of those orbitals together so you can see how they stack. They stack like those dolls that you see at Christmas time, where one doll goes inside of another doll, goes inside of another doll, and you get all of these dolls all stacked together. And that's pretty much how orbitals are. They kind of stack in that regard, but they stack according to their shapes, the S, P, D, or F. So let me show you this. Not my video, obviously someone else's video, and they did a great job at animating this. I love it. So flying in right now, we see 1s, so that's a small sphere. Now we see 2s, that's a larger sphere, and it's going to go on top of our 1s. Again, this is where electrons live. We're building where they live. Now we've got a 2px, that's the x orientation. We also need our y and our z orientations from the balloons from before, if you remember. All right, I can't keep up with the video, it's too fast. It's too fast! No! All right, so, nope, I'm still missing one. Okay, so now we go on to 3s. And 3s encompasses all of that P, the 2P, the lower energy. Now we've also got 3P, so there's even bigger peanuts out there. Bigger P levels that are stacking on top of the other P sublevels on the X, Y, and Z orientations. Oh, the balloons are going everywhere. All right, we've got a 4s coming in, and it's encompassing all of the other stuff. Look, it's stacking so nicely. Look at all those places where the electrons live. Now we're finally seeing the D's come into play. Here's our daisy dumbbell. No, here's our donut dumbbell, and our daisy is now coming in, one of our daisies. Now, remember, we still have other daisies coming in. So here's another daisy, and another daisy, and they're quite large because they're level 3. And another daisy, also quite large for level 3. And there you go. So this is someone's rendering of scandium for a orbital shape model. You can see how they all stack together. And again, this is where all of the electrons are living. So now that you've seen kind of how these orbitals look and how they can stack on each other, now we're going to try and draw them ourselves. So now we're going to attempt to draw this clearly in an XYZ plot. And in order to do so, please keep in mind that even if you don't have enough electrons to fill all of the orbitals, if you're in the p block, you still have to show all 3 p orbitals, all 3 orientations for p, even if they're not all filled. So if you're that one lucky electron living in the Family Guy's household, if you didn't catch that reference, please go back and watch my other video on electron configurations to understand that. What we can see then is that we still have a Family Guy household, but with only 1 electron living in it. You can't just take off an entire chunk of Family Guy's house. Let's give it a try. So we're going to first find the electron configuration for aluminium, and then be able to use that for its orbitals. So we first need to find aluminium on the periodic table. It is right there. And in order to write its electron configuration, we're going to go to level 1, S2, 2, S2, jump over to 2 over here, 2, P6, 3, S2, and we're still in level 3, but now P1, 3P1. So let's write that out so that you got it. We've got 1, S2, 2, S2, 2, P6, 3, S2, 3, P1. That would be our electron configuration for aluminium. Now that we know what its electron configuration is, we can also write its orbital shapes. In order to draw the orbital shapes, we need an X, Y, and Z plot. So we have X, Y, and in chemistry, we use a wedge to show things coming out at us. So that would be coming out at you. That would be your Z. And we use dashes like this to show things going away. This would be our 3D plot. What we need to draw now is 1S. S is a sphere, and it's a small sphere. So I'm going to draw that in the middle like that. Now we need to move on to 2S. 2 is slightly bigger, but still a sphere. So we need to make a bigger sphere, like that. Now we have 2P. To pee or not to pee? That's frequently the question when you're pregnant. More or less 2P. 2P6, we have 3 orientations. Those are our peanuts, P for peanut. So we have the same size of 2, but in the orientation of a peanut. So we're going to go up to 2, like a peanut, on the Y. We're going to go peanut on the X. And now we need to go peanut on the Z. All right, well, that's already looking like a flustercluck, if you know what I mean. Let's move on to 3S. 3S2. S is sphere, so larger than the last ones. So spherical. And 3P1. 3 is going to be the same size as the S sphere, but has the orientations of peanuts. Now, even though there's only 1, we still have to draw all 3 orientations. So that would be our Y orientation peanut, our X orientation peanut, and our Z orientation peanut. It's beautiful. Those would be your orbital shapes for aluminium. Go ahead and give this one a try yourself. Draw the orbital shapes for neon. I encourage you to pause the video here and give it a try. For all of you rebels out there that are refusing to pause, we first need to write the electron configuration for neon. right there. And neon is 1s2, first level, over 2, 2s2, right there, 2p6. So this one should be a little easier to draw than the one we just did. You're going to need a y, x, and z plot. And now we're going to add in our shapes. We have 1s, that's a sphere, that's small. We have 2s, that's a slightly larger sphere. And now we have our peanuts. We have 2p6. So it's going to be the same size as the green, but we're going to have peanut on the y, peanut on the x, and peanut on the z. That would be your orbital shape for neon. Now that we know what the shapes look like and how to piece an atom together based off of these shapes where their electrons live, we can also write orbital diagrams using our electron configurations or just using our periodic table. An orbital diagram shows the energy level based off of this side over here. So you can see that as we go up, the energy increases, and also shows the placement of electrons. We're going to put electrons in these boxes here. The s orbital, as a reminder, can fit 2 electrons. So anywhere where there's s, you can only fit 2, a max of 2 electrons. Anywhere where there's p, you can fit a max of 6 electrons. Anywhere where there's d, you can fit 10, and so on and so forth. So in an entire level, if we were going to look at, say, 2s, 2p, the max that it could fit in level 2 would be 8. That's 6 plus 2, or 6 plus our 2, to give us 8. As we go higher on this orbital diagram, it also means increasing higher energy. When we fill an orbital diagram, we have to fill it according to the Pauli exclusion principle. This implies that electrons spin. So in order for 2 electrons, which are both negatively charged, in order for them to tolerate each other's presence, they literally have to spin in an opposite direction from each other. So if one is spinning this way, the other... Wait a second. I'm not going to be able to do this. Hold on. There we go. If one's spinning this way, the other one's going to have to be spinning the other way. So it is an opposite spin in order for them to live in the same household, the same orbital together. That's the Pauli exclusion principle. The way we represent those opposite spins is with opposite facing arrows. So the way you could see this is full arrows going up and down as I've depicted there, or sometimes you'll see people draw them like this. Both are fine. Both are completely fine. They just represent each an electron. So that's an electron and that's an electron. One is spinning to the left, the other spinning to the right. You can kind of think of it that way. They're spinning in opposite directions, represented by the up and down arrows. So some steps you need in order to fill an orbital diagram. You need to fill 1 electron at a time per box. Then go back and pair them up. In each box, you can only fit a max of 2 electrons. And remember that each electron has an opposite spin. So when we draw in electrons, we're literally drawing in arrows to represent them, one pointed up, one pointed down, according to the Pauli exclusion principle. And then we're going to completely fill each level, so we wouldn't jump from 1 to 2 to 3, before going through 2 and then to 3. We're going to fill each level before moving up. As always, I like to give you a breakdown of steps. So first, you need to locate your element on the periodic table. Draw an orbital diagram like the one on the previous slide where you have an energy arrow with a bunch of boxes. You're going to draw the 1s box always lowest on your paper, so all the way at the bottom, it is the lowest energy level. And then you're going to draw the boxes increasingly higher energy levels. Then you're going to put in your electrons up and down according to the Pauli exclusion principle until you get to the atom of interest. Let's give it a try for potassium. First step is to locate potassium on your periodic table. So with your periodic table, you see that K is located right there in level 4. Awesome. Second step would be to draw this orbital diagram, which I've already drawn for you. It's there. So kind of one of those things I just recommend having in your notes or having nearby if you're being tested on orbital diagrams, so you know how to draw this quickly and fill it in. Then we need to figure out, well, how many electrons do I have to fill in? For K, for potassium, I have a total of 19 electrons. How did I get that number? 19 because that's the atomic number. If you don't remember from a previous lesson where I talk about the atoms, their protons and electrons, please click on the card that's there or the link in the description below to refresh yourself on why 19 is representing not only the protons but the electrons for potassium. So we know that potassium has 19 electrons, 19 E minus, because electrons are negative. So we know we need to fill in our orbital diagram from the bottom to the top until we get to the number 19. And we need to do that with up and down arrows. So I'm going to go 1, 2, 3, 4. Now I'm getting to the point where I have multiple boxes, so I need to go across before I go back and pair them up. Let me show you what I mean. 5, 6, 7. Notice how I went across first before I go back and fill them up. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. That would be our orbital filling diagram for potassium. You could use this to quickly write the electron configuration. 1s2. There's 2 electrons in there. 2s2. 2p6. 2, 4, 6. 3s2. 3p6. 4s1. Pretty cool. So if you were going to look at the previous orbital diagram and what I have now above my head, they would be identical. And you can also see that I've written out what I wrote before, all in one electron configuration right there for you, all in one line. Let's give it a try for the other following elements. As usual, I encourage you to pause the video here and try an orbital filling diagram for helium, boron, neon, and aluminium. Helium is right here. Helium has an atomic number of 2, so it has 2 electrons to fill. 1, 2. Done. That would be the orbital filling diagram for helium. Let's try boron. Boron is right here, and boron has 5 electrons. So 1, 2, 3, 4, 5. Great. That would be the orbital filling diagram for boron. Now, if I wanted to also write out the electron configuration from this, it would be 1s2, 2s2, 2p1. Now, if you remember from a previous video for electron configurations, I said that the D block is 1 level below and the F block is 2 levels below. We represent that on our orbital filling diagram by, once we get to D's, notice that the D is sandwiched between the 4s and 4p. So it's still a little bit higher energy in terms of increasing energy than, say, 3p would be. When we look at 4D, 4D is sandwiched between 5s and 5p. Now if we go up to the F, we can see that the 4F is actually sandwiched between your 5p, 6s, and 5d. Oi! If anything, I encourage you to copy down this diagram right here that has all of the levels ready for you to go in a format where you can just plug and chug. Just like in the electron configurations where you could determine the valence and therefore the charge of the atom, we can also use the orbital diagrams to do the same. We can write our electron configuration or draw the orbital diagram, or draw the orbital diagram, then write the electron configuration, whatever you're more comfortable with. Use that octet rule again to figure out how far away it is from 8. Then you need to add or subtract in order to get to 8 or back to 0 in order for that atom to be like the noble gases. Then you're going to write the new electron configuration using your orbital diagram for the charged atom. So this is where an orbital diagram is really helpful, because you can see, well, how many electrons do I need to boot out, or how many do I need to add in? And then you have a completely new electron configuration for a charged atom as opposed to a neutral atom. So let's give this a try in terms of using our orbital diagram, electron configurations, and everything we've learned thus far in order to determine the ion of aluminium. As a reminder, the word ion means something with a charge on it. So an unneutral atom, a not neutral atom. So aluminium with a charge on it. We want to figure out what its charge will be. So just like any other time, we got to look at our periodic table first to orient ourselves and find aluminium, which is right there. If we're going to jump in and fill in this orbital diagram, we would note that aluminium has 13 electrons. We're going to start from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we've got 13 electrons filled. Now this would be the orbital filling diagram for a neutral atom of aluminium. The question is asking for the charged aluminium atom, for the ion. In order to do that, we need to figure out if it's more convenient for aluminium to gain extra electrons to become like a noble gas, or to lose electrons to become like a noble gas. Let's figure out what it wants to do. First, let's write out what its neutral electron configuration would be. It would be 1s2, 2s2, 2p6, 3s2, and 3p1. Great. So we can think about this two ways. We can either use the previous knowledge of looking at our highest energy levels, that would be our 3s, and adding our 2 plus 1. We could also figure out, well, how much farther am I away from filling this orbital diagram? I could either lose 1, 2, 3 from my higher energy levels, or I would have to gain 1, 2, 3, 4, 5. Oi! So the idea is either I'm gaining 5 electrons or I'm losing 3 electrons. It's a lot easier to lose the 3 than gain 5 to have a full octet. Since we are going to prefer losing 3, it's going to take the path of least resistance. Losing 3 negatively charged things, just like if you were upset about 3 things in your life, you were a negative of 3, you lose those 3 negative things that are bothering you, you become positive 3. So now aluminium is going to become plus 3 charge. In other words, its ion will be Al plus 3. So now that we know that aluminium would have a plus 3, it would be an ion of plus 3 charge, what would its new electron configuration look like for a charged atom of aluminium? This was the neutral electron configuration from before. But once it's charged, I would lose my 3 electrons in the outermost orbital. So essentially, I would be losing this end part. So for a charged atom of aluminium, its electron configuration would actually be that. Just subtracting out those higher levels and erasing them entirely. So we would actually end up looking like neon. This is technically the electron configuration for neon. Pretty cool, right? In other words, in aluminium's mind, if it has a +3 charge, it can be just like the noble gas, neon. So how does my previous lesson and this lesson all fit together? Electron configurations tell you what orbitals there are and how many electrons there are. So it tells you the levels, the shape, and how many electrons are in those. The orbital diagram tells you more about the energy of the orbitals because we're looking at a diagram that specifically has energy on the y-axis and then boxes along the side with increasing energy. Whereas the electron configuration implies that by the levels, the orbital diagram shows that better. And it also shows where specific electrons are located with their ups and down spins. In an orbital diagram, we also have each box itself representing a shape, a specific shape. So if we're thinking about the S, and then the P's, each one of these was one of those peanut shapes. So we had an X, Y, and Z axis. So each box is representing a specific shape. We can also use this to determine a charged atom's electron configuration. And then, of course, those shapes that we were drawing on our X, Y, and Z axis plots that looked really funky, those are going to tell you what an atom looks like at an atomic level. So now, hopefully, after watching the previous video and this video, you should be able to write a long electron configuration for sulfur, a short electron configuration, determine its valence, determine the charge it would make, the orbital shapes of sulfur. You should be able to write out the orbital diagram for a neutral atom, and also the orbital diagram for a charged atom. Let me know if you have any questions in the comments below. I'd be happy to help. If you're feeling in the giving spirit, please click on that subscribe button for me and throw a duck some bread. Thanks. Have a ducky day.
No ducks, no glory.